Okay, guys, so today we're actually going to be talking about the Laplace transform and use that to solve a first order differential equation. So, the actual purpose of a Laplace transform is to take essentially a differential equation and turn it into an algebraic equation so it's quite simple to solve. So, let's take a look. So, the Laplace transform of a function f of x is just equal to the improper integral from 0 to infinity of the function f of x times e to the negative st dt. And the resulting transformed function will be in terms of s, and we'll call that capital F of s. And taking a look at our most easy example, let's try to transform e to the at, which is just the Laplace transform of a function f of t. And this is just equal to the improper integral, again from 0 to infinity, of e to the at times e to the negative st dt. Now what this does here is quite simple. It's the same base, so e to the a minus s times t dt. Rewrite the integral like this, and then integrating will give us, and we're actually defining this for all s greater than a. And that would just give us evaluated from 0 to infinity. And the way we do that is by taking the limit as b approaches infinity of e to the a minus s times p all over a minus s minus e to the a minus s times the 0 over a minus s. And if you will notice, since s is going to be greater than a, our exponential actually turns into a decreasing exponential function. So the limit as b approaches infinity, so at infinity, it would actually equal 0. So this would actually become 0. So we have 0 minus, and the 0 on the exponent just makes it a 1 over a minus s. So that's just equal to 1 over s minus a. And we'll say that's equal to the Laplace transform of e to the at. So that's the most simple and quick example of how the Laplace transform actually works. So now what I want to do is actually try to apply this to a differential equation. So if I look at y prime minus ay equals 0, an arbitrary differential equation, I can write this as dy over dt minus ay equals 0. Now, what we want to do is transform this entire equation using the Laplace transform. And essentially, transforming the entire equation is just taking the Laplace transform of each individual term. So that's just equal to, remember dy dt is just a function, and the Laplace transform of 0 would just be 0 because, yeah, the integral cancels out. And let's just worry about this part for now. When we look at that, we're actually integrating from 0 to infinity of dy over dt times e to the negative st dt. Now this looks a little complicated, but it's not very complicated because we can use integration by parts quite simply here. So we're actually going to be integrating this guy and differentiating this guy. So uv minus integral v du equals integral of u dv. So that's just going to be y times let's see here, e to the negative st minus integral of y times negative s e to the negative st dt. I'm going to actually pull the s's out to simplify this a little bit. So, of course, evaluate everything from 0 to infinity here. So, pulling this out would just become a positive s here, and y times e to the negative st dt. Actually, what you want to see here is that you might think, oh, there's another integral for me to do here, but not quite. If you notice, this is actually just the equation for the Laplace transform of some function y. If I were to tell you to take the Laplace transform of y, you would write this as and this is exactly what we have up here. And I'm going to make a disclaimer here that earlier, remember, when I took the Laplace transform of the function f of x, I said the resulting transformed equation would be capital F of s, a function of s. So in this case, we can actually say capital Y of s would be the transform of y. And actually, for that matter, we can even say, yeah, I mean, just keep this in mind. Just keep in mind that this is equal to the Laplace transform of y. This is just makes it easier to write. Yeah, now, don't forget to evaluate this, of course. So, evaluating this guy from 0 to infinity would just give you a 0 minus y, correct? Because of the s pushing it to the bottom. So you would just get negative y, and then that's at 0 because we plugged in a 0 for t. So y naught plus s times we said this entire guy right here was just the capital Y of s, the Laplace transform of y. So that's just our Laplace transform of dy dt completed. And now with the remaining terms, so remember our differential equation here was dy dt minus ay equals 0. So now we finished transforming the dy dt, transforming the ay. Remember, I just said the transform of y is just capital Y of s. So we can actually just attach this, so we can say y naught plus s, and then minus a times capital Y of s. Remember, y's transform is just capital Y of s equals 0. And now let's actually solve for capital Y of s, which is the transform. And that can be easily done by some algebraic manipulation here. So let's see here. Capital Y of s is just equal to y naught over s minus a. So this is our fully transformed equation here, capital Y of s. Now you might wonder, how does this actually solve the differential equation for me? Now what you got to remember is we actually transform this into a simpler form, which is just an algebraic equation. Now what we have to do here is actually do the inverse Laplace transform. In other words, so here, inverse Laplace transform. In other words, that just means that you're thinking of which function's Laplace transform actually gives me this. And if you'll recall from the example at the beginning of the video, I did the transform of e to the at, and that actually resulted in 1 over s minus a. So you'll see the correlation of that to my result over here, which is just y naught divided by s minus a. So that's really, when you take the inverse Laplace transform, it's just saying y naught times e to the at. Remember, inverse Laplace transform is just trying to find the function whose transform looks like the one you solved for. And that function would be e to the at. So you just multiply your initial condition y naught with e to the at. And this is just our solution to the equation y prime minus ay equals 0. And I'm pretty sure you guys recognize this solution, as it's a very common first order differential equation solution. So I'm going to actually show you a little bit of, this was all arbitrary theory, right? It's all these constants. A is an arbitrary constant, dy dt was an arbitrary derivative function. Now what I want to show you guys is actually an application of this theory, or at least compare this to a more traditional method. Now consider a physics equation here. We have our, let's say, f equals ma, and then acceleration first derivative of velocity, so m dv dt equals, and let's say our forces acting on an object is just drag force. And drag force is all that's acting when your object is at terminal velocity in free fall. So drag force is just equal to negative bv, where b is the drag constant, or drag coefficient, sorry. So this is just equal to negative bv, and this we have a differential equation. Now let's try, this is a first order equation. First order equation, diff eq. Now let's try solving this using separation of variables, which is, I'm pretty sure you guys are already familiar with that. So in order to do that, I'm just going to, let's see, I'm going to dv over v equals negative b over m dt. So I got all the variables to their own separate sides, and here we can actually just integrate. So this is from 0 to t, and this is from v naught to vf. And vf is our terminal velocity, which is what we're solving for. So ln of vf over v naught is just equal to negative bm over t. And I'm sure you guys see that it's just when you evaluate the bounds, it's the same thing. So exponentiating both sides just gives us vf over v naught equals e to the negative b over mt. And then solving for vf just gives us v naught times e to the negative b over mt. Look at that. Doesn't this look a lot like our solution using the Laplace transform? Look at that. I'm going to put it right next to each other. Okay, so again, I told you y naught, or y of 0, y0 is just an initial condition. And in our case, where we're actually thinking about it in context, v naught, or velocity initial, is our starting condition. So that matches. And then e is just e, and then a is just, again, I told you it's an arbitrary constant, but when you add application to it, it is negative b over m, negative b being the drag coefficient and m being the mass. So a is just negative b over m, and then you have the t. Look at that. So you can see how many methods yield the same result. So if I wanted, I could actually solve this physics diff eq using the Laplace transform, that would also result in the same thing. So I hope this provided a good introduction to what the Laplace transform actually is and the intuition behind it. And stay tuned for future videos where I go over second order differential equation with the Laplace transform. Thank you.